Hello! So in this video, we're going to just do sort of a quick introduction video on the sort of notions of convergence when it comes to series. So we've discussed a lot about ideas of convergence when we did sequence and series, we did limits, we did differentiation, which was types of limits. We've talked about integration, again, types of limits. But a lot of the time when doing this, it gives this idea that, this idea of convergence is like, oh, epsilon deltas or maybe capital N's and things, and this is just sort of the way it's done, and we sort of just merrily march along. And it's really at the point of series where I think it's worth taking just a quick second to understand why we go through as much sort of rigor as we do, right? Because a lot of the times we're like, oh, what's the limit as x goes to 2 of x squared? And we go through all this epsilon delta nonsense to be like, it's 4. What a shock, I could have just plugged that in, right? And even when it's stuff that you couldn't plug in, a lot of the times the examples we use, because we're trying to learn this stuff, are intuitively accessible enough that it seems like we're going through a lot of this rigorous effort for something that is intuitively obvious. And the question is, why do we need to bother, right? And so series, in particular, sort of historically speaking, this is one of the main reasons why a lot of this stuff was developed the way it was, with the epsilons, deltas, capital N's, all of this stuff. And the reason why is because before it had a rigorous backdrop to it, a lot of people were making very sensible, very logical, very intuitive arguments and coming up with different answers. And that is not a thing we want to have happen in math, right? We want to be consistent, and we want to know the answer is right, even if we have to go through some extra rigor to get there, okay? So, as just a footnote here, this stuff is actually a lot more recent than a lot of people realize too. So a lot of the sort of stuff that as we do it today, when we talk about convergence, again, epsilon deltas, capital N's, a lot of that stuff was developed by a mathematician named Cauchy, who is exactly that person that you saw when we did sequences and you did Cauchy sequences. It's that guy, okay? But he actually, he lived from the late 18th, early, really 19th century. So this stuff is, this whole idea of convergence, the epsilon delta stuff, it's about 200 years old, which, that seems old. But if you think about it, that means that America was America, let alone like a colony of Great Britain, before we actually understood how to do convergence. So in the scheme of, addition, like, talk about Pythagorean theorem, millennia old, right? Thousands and thousands of years old. In the grand scheme of mathematics, this is really quite recent. And so in this video, I just want to give an example of one of these sort of intuitive arguments giving a bunch of different answers. So for the whole idea about a series, right? So if you remember from, calculus 2, the series is adding infinitely many terms. But nonetheless, we're just adding these terms, right? And so historically, again, before we had sort of a nice rigorous backdrop to do this, people would make these arguments that, adding is adding, whether you're doing it with 5 things, 2 things, or infinitely many things. So for example, let's look at sort of a classic conundrum series here. So let's look at the series, meaning adding infinitely many things, of 1 minus 1 plus 1 minus 1 plus 1 minus plus, etc. Right? So I add 1, then I subtract 1, then I add 1, then I subtract 1, then I add 1, then I subtract 1. On and on and on, okay? So I'm going to do this. I'm going to get 4 different answers without any advanced mathematics at all, okay? So I'm going to try to convince you with very logical arguments that use no advanced mathematics whatsoever, kindergartner level, that this has an answer, but 4 different answers, okay? So the first thing I'm going to do is say, okay, well, I can add infinitely many terms, but I can add things together any way I want, right? So for example, remember, right, the, let's say commutative law, right? So we have A plus B plus C. I could do that instead as, say, A plus C plus B, right, where I'm really doing those two first instead of those two first, okay? So that's really associativity and commutativity. But the point is I can rearrange addition. So what if I did that here? What if instead of having 1 plus negative 1 plus 1 plus negative 1, that's how I'm going to think of it. Instead of doing that, what if I did, say, 1 plus 1 plus 1 plus, I'd do that a whole bunch, but then I'm going to have negative 1 plus negative 1 plus negative 1 plus negative 1, etc. Right? So I have a bunch of positive stuff being added together. In fact, I have infinitely many. And then I have infinitely many negative things being added together. So that's infinity plus negative infinity. And that's not a thing, right? We learned about that even in calculus, where if you ended up with some limit that looked like infinity minus infinity, that was just undefined, right? That was one of your indeterminate forms. So this seems to be an argument, right, with doing nothing more than commutativity, that trying to add together this series should give me something indeterminate. But okay, hold on a second. Maybe you're thinking, okay, well, yeah, but this whole dot, dot, dot in the middle nonsense is not cool, right? How could I move infinitely many things in the front and then start doing something with infinitely many other things? And that's fair. So instead, let me do a different thing. So just like up here, right, we have the associativity law, which I'll also write. So if I do normally A plus B plus C, that's the same as doing A plus B plus C, right? So whether I added the first two first and then the last one, or the second and third one first and then the first one, I should get the same answer. So I'm going to do the same thing here. So instead, I'm going to take this thing, I'm going to do 1 plus, and then I'm going to group these two things together. So I'm going to get negative 1 plus 1 plus, and then I'll do the same thing with the next ones. Negative 1 plus 1 plus, negative 1 plus 1 plus, etc. But this is really 1 plus 0 plus 0 plus 0, right? This is just 1. Right, because I just have 1 and then everything else just sort of eliminates itself. So I get 1 plus 0 plus 0 plus 0, infinitely many zeros. So the answer is clearly 1. Okay, that seems reasonable. I mean, I didn't do any like shenanigans with moving infinitely many terms around. In fact, all I did was decide how to add these things, and I did that with finite things, right? I only paired things together. But what if I, instead of doing 1 plus and then paired together, I did something like 1 minus 1, right? I paired the first two, plus 1 minus 1, plus 1 minus 1, plus, etc. Right? But now I have 0 plus 0 plus 0 plus 0 plus 0. Now I have 0. That's not good. That's not good at all, right? Because I've done the same technique. All I did was pair things up, right? Just like I did up here. But now I have a different answer. That's concerning. But wait, there's more. What if I took, for example, one of these things and moved it out, and then I started pairing? So I ended up with something like negative 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, etc. Right? So essentially I maybe flip these two, right? So I isolated that, flip those two, pair, and then flip the next two and pair, flip the next two and pair, right? So I'm flipping each pair and then pairing up the result. That would get me this series, and this is negative 1. Again, this is kind of concerning, right? Because again, I've done commutativity, which should be a thing. I've only done it with pairs of numbers now. I haven't done some infinity shenanigans. And I paired things up, which again is associativity, right? I should be able to decide the order I want to add things together. And again, I didn't do associativity across infinitely many things. I just paired things together. And yet, doing just pairings of commutativity and associativity, I've now got 3 different answers. This is pretty concerning, right? So this one series could be 1, -1, 0, does not exist. I mean, I've come up with fairly logical, intuitive, straightforward ways of showing that all of these should be valid answers. But that's not how we want math to work, right? We need math to give us sort of a definitive answer. We need it to either not work, or if it works, it is consistent in how it works, right? There's plenty of things in math where we try to do something and it just doesn't work. That's life. But if it works, if I can make an argument and come to a conclusion that is valid, that conclusion should be the same conclusion anyone else comes to under the same circumstances. And that's just not happening here, right? So this is exactly the sort of problem that Cauchy was actually trying to solve, that he was sort of trying to tackle, is how can you take something that has such intuitive arguments that seem logical, straightforward, and mathematical, but give you different answers? How can we stop that from happening? How can we come up with a system, a set of requirements that forces everybody to get the same answer every time, when it seems like even the most basic of rules could get you different answers, okay? And so the answer to that really is that we come up with a very rigorous definition of what it means to converge for an infinite series, and we require that that definition be the one that you satisfy when you're trying to show that a series converges, even when sometimes it gives you an unsatisfactory answer, right? There are times where it seems like a series should converge intuitively, but under this definition it doesn't. And it's because sort of not having that sort of rigorous background guides you into this kind of difficulty where something that seems so intuitively obvious, it turns out could be sort of a death trap and cause all kinds of nonsense, okay? So this is, like I said, this is sort of a fairly informal, but an introduction to the idea. This is sort of motivating why it is that we're going through all the work that we're going to be going through and have gone through when we talk about the rigorous ideas of convergence. It's not just being nitpicky math people, it's that we really are trying to solve a problem of trying to sort of have the framework so that everybody gets the same answer every time, no matter how you got about getting there, okay? And that is it.